Hi everyone, my name is Lina Rahmaningrum and I am honored to be here today to share our research on life cycle cost analysis of pavement types for national roads in Aceh. This work is a collaboration with my esteemed colleague Aristiawan and Florentina Punggi Pramesti from the Department of Civil Engineering at Universitas Sebelas Maret. Infrastructure decisions are not just about initial costs, they are long-term investments that shape our communities and impact our economies. Our study aims to provide a comprehensive understanding of cost implications over the lifespan of different pavement types, empowering more sustainable and cost-effective decision-making. I am excited to take you through our findings and explore how strategic choices in pavement design can drive more resilient infrastructure for the future. Roads enable the transportation of people, goods, and services, in addition to providing access to land and supporting commercial and social activities. Although essential, pavement projects globally are often hindered by delays and exceed their budget, causing public resources to be utilized ineffectively. The Pavement Gerbang Road, a national unpaved road in Aceh Tengah Regency, Aceh Province, Indonesia, is an example of such challenges. This road connects Gempang district with Takengon city and serves as a vital economic link. However, its deteriorating condition has made it one of the poorest maintained national roads in the region. According to the Aceh National Road Agency, the road's unpaved road condition index or UPCI is 15.61, classifying it as requiring reconstruction. The UPCI, introduced by the Chilean Ministry of Public Works in 2007, provides an objective method for assessing unpaved road condition based on distress, drainage, and profile characteristics. As noted by M.Y. Sahin, roads with such low condition index must undergo reconstruction to ensure safety and functionality. Previous studies have analyzed the performance of and life cycle cost of flexible and rigid pavement using life cycle cost analysis or LCCA. Some studies have indicated that the life cycle cost of flexible pavement is lower than rigid pavement, whereas others have reported the opposite. According to G. White, while rigid pavement may be more cost-effective in the long run provided it doesn't require immediate and expensive reconstruction, flexible pavement is more economical in the short term. Rural road networks are crucial for economic development, especially in developing countries, where they are key to transporting agricultural goods, reducing poverty, and enhancing access to essential services like markets, school, and healthcare facilities. Given this challenge, this study aims to determine the most cost-effective approach for reconstruction the Pavement Gerbang Road. This study aims to provide insightful information that will help engineers and policymakers make well-informed decisions about the construction and maintenance of road infrastructure. This study focused on the Pavement Gerbang Road located in Aceh Tengah Regency, Aceh Province, Indonesia. The analyzed section spans from Stationer 0 to Stationer 5 and is classified as an unpaved road. Due to significant deterioration, an evaluation is necessary to assess potential reconstruction alternatives. The UPCI is employed to examine the condition of unpaved road. The average UPCI value for the Pavement Gerbang Road was recorded at 15.61. and is classified rating very poor. This dataset includes information on road classification, traffic road rate, road width, number of lanes, pavement type, and pavement thickness, and the average annual daily traffic data. Analysis. The life cycle cost analysis method was utilized to identify the most economical solution for road reconstruction. The integrated LCCA framework, adapted as recommended by the Federal Highway Administration or FHWA, is illustrated in figure number 1. First, we have to establish alternative pavement design strategies, and then determining performance period and activity timing, estimating agency and user cost, developing expenditure stream diagrams and computing net present value, and then analyzing result and re-evaluating design strategies. The collected data form the basis for alternative design. Subgrade CBR determines the road foundation, while traffic data define pavement layer thickness. Traffic loads are represented as ESA4 for unpaved road, ESA5 for flexible pavement, and heavy vehicle axle group for rigid pavement. The design surface life is 10 years for unpaved road, 20 years for flexible pavement, and 40 years for rigid pavement, designed for each alternative based on ASTO. Calculations are shown in Table 5. While the maintenance scenarios can be seen in Table 4, there is an activity routine maintenance, periodic maintenance, and reconstruction. Here, the rigid pavement doesn't require the routine maintenance. Figure 3 illustrates the 40-year analysis period, with year 0 representing the initial cost of improving the Pavement-Gunting Road. Reconstruction occurs every 10 years for unpaved road, every 20 years for flexible pavement, and is not required for rigid pavement. All alternatives undergo annual routine maintenance, but these costs are not shown in the expenditure diagram as they are relatively similar. By the 40th year, all alternatives are assumed to be severely damaged with a residual value of 0. The result aligned with several previous studies. Jonas found that flexible pavement 7.9 million ETB more than rigid pavement. According to Ario, employing different material combination may lower LCCA expenses while also improving the functionality of flexible pavement. And Abdur found that flexible pavement has a greater total LCCA than rigid pavement. The conclusion for my research is this study compares the life cycle cost of unpaved road, flexible pavement, and rigid pavement for the Pavement-Gunting Road. Unpaved roads have the lowest initial construction costs within Indonesian rupiah 5 billion, but their frequent maintenance leads to the highest long-term costs. Maintenance costs are Indonesian rupiah 27 billion for unpaved roads, Indonesian rupiah 22 billion for flexible pavement, and Indonesian rupiah 0.46 billion for rigid pavement. Vehicle operating costs or VOC are also highest for unpaved road. Indonesian rupiah 108 billion compared to flexible Indonesian rupiah 90 billion and rigid pavement Indonesian rupiah 87 billion. The total life cycle costs are Indonesian rupiah 140 billion, Indonesian rupiah were 124 billion, and Indonesian rupiah 170 billion for unpaved, flexible, and rigid pavement respectively, with a cost ratio of 1/0.9, 0.89 over 0.84. Given these findings, upgrading to rigid pavement is the most cost-effective solution, minimizing long-term expenses while ensuring sustainability. Future research should explore environmental and social impact, traffic growth, and maintenance strategies to enhance long-term road management and investment planning. I would like to express my gratitude to my co-authors Aris Tiawan and Florentina Punggi Pramesti, and to Universitas Sebelas Maret for their continued support. Thank you for your attention. I am open to any question or discussions you may have. Thank you.